New one for us today. Well, actually, where did we finish off last time? Let's see. Was it this one? Yes. No. This one. Okay. Where did we finish off? Uh-oh, I see Tyler up there. Okay. We talked about ionization energy. Okay, cool. So we will start then today, with electron affinity. Alrighty. Good morning, everyone. Let me just pull up a table here. Let's do it on this. Yes. Do I like this table? No, I don't. Okay. Well, regardless, I guess we'll just show it anyway. Okay, here we go. Electron affinity. So, actually, I guess I should define it, huh? So, previously we talked about ionization energy, right? And that was the energy that is required to remove the outermost electron. This is now the energy to gain an electron. And typically, this is exothermic. So we saw that it always takes energy to remove an electron. So ionization energies were typically endothermic. We're going to see that electron affinities are typically exothermic. And so let's just go ahead and have a look at a few of these numerically speaking. Oh, why am I showing myself? That's really meta. Okay. So these actually all have the opposite sign on this particular one, and that's just pretty common, but understand that these should all be switched signs. So fluorine, for example, here actually would release 328 kilojoules per mole. So they've just kind of flipped the sign here. But let's take a look at some of the trends here. So first of all, we notice that the noble gases, all on the other side. Hold on, Preacher's barking outside. Let me go bring him in. Preacher, shush. Preacher here. All right, I have brought the culprit back. Naughty creature. Yeah, grumble all you like. Okay, so we're going to see that all the noble gases, of course, do not want to gain an electron. So doing so for any of these would be pretty unfavorable. And we're going to see that our nonmetals typically will want to gain electrons, right? Especially these halogens over here. So we see that these will actually release quite a bit of energy when they gain electrons. And we're going to kind of see the same trend just going on here. By contrast, if we look at our metals, we see that a lot of these have very small electron affinities. Just by comparison, I mean, here's calcium with 2, titanium with 7, strontium with 5. Some of them, in fact, would not even want to gain electrons at all. It's unfavorable for that to happen. So we're going to see just generally, again, fluorine is going to be our, fluorine and chlorine here are going to be the ones that are going to be wanting to gain the most electrons. It's just most favorable for them. Let's look at a couple of these interesting negative spots here. We see negatives in group 2, in group 7, 12, and 18. Why the heck do we think those ones would be particularly not happy to gain electrons? So let's just go ahead and think about these. So we've got beryllium, manganese, zinc, and helium. So let's look at those. How do I get out of this? Oh, I'm on the wrong side. Okay. Let's take a look at here are 4 of them that don't want to gain electrons. So, if we notice, if we look at the kind of last electrons, we're going to see that these ones will not want to gain anymore. Exactly. So Kevin has it right on the head there. So remember that manganese. Here's the creature. He's very upset. Okay, manganese, remember, already has. It's got a half full shell. Oops. Remember, half full is favorable. So it does not want to become like iron and stick another electron in. It's not going to happen. Or it's just not going to be favorable. You could force it to, but unlikely. Same thing here. Our zinc has a full D shell. It's not going to want to put any more in. So we're going to see kind of, remember those blips that we had with ionization energy? It's the same thing for electron affinity. So when we mess with the stable shells, that's when problems happen. So we like to have things that are full, half full. I guess I should half full or empty. These are happy times. And so we're going to see that messing with one of these 3 states is not a good thing. So generally we're going to see the following 2 things. There's not an obvious trend for us this time, but just know that non-metals typically have large exothermic electron affinity. And then we also saw that the noble gases and we also saw that those metals kind of are on either side. Okay. Opposite. So, Shane, remember that ionization energy was always positive. Ionization energy was the energy to lose an electron. If we think about it, remember we were able to zap our atoms with X-rays and knock electrons away, the photoelectric effect. We had to put in energy to do that, right? For your solar panels to work, you have to shine sunlight on them. Sorry, creature's getting very angry. Look at him. So angry. Yes. Okay, onto the couch with you. Ugh. Okay. So remember, here is our solar panel. Solar panel. Look, here comes some energy from the sun. Out comes an electron. Ionization always is endothermic. That's not a very nice is. Let's redo that. So we always have to put in energy to blast out an electron. So think of it like a solar panel. You need your sun to zap it. Zapping it will kick out electrons, which can then go do our lovely electric tasks that we need them to do. So ionization is always endothermic. Okay, for electron affinity, it's not as obvious. It could be exothermic or endothermic. Yeah, just typically the non-metals will have exothermic ones. They want to gain electrons. It's favorable for them to do that. And it's going to be the opposite for the metals. I'm sorry, yeah, kind of. And then the noble gases just do not want it all to gain electrons. Alrighty, so we have a reaction here that we're familiar with, perhaps. This is technically the same thing as saying technically, this is kind of the electron affinity. For this particular one. So this is like how these reactions are happening. So this one here is endothermic. This one here is exothermic. Let me go ahead. Let's see. Will it make sense for us to do a Hess's law problem with this? Probably. Let me just look up the numbers. Here it is. Where's our happy chart? Okay. All right. Cool. Actually, does it make sense for us to do this? No, there's no purpose. You guys have done Hess's law already. Forget it. Okay, but just so we know, these are what these reactions would look like. So ionization versus electron affinity. Okay, so happy times. Did we talk about electronegativity yet? I don't remember. Maybe. I don't remember if we did or not, so someone let me know. If not, it's the tendency of an element to it's related to covalent bonds. Okay, cool. So technically we're going to learn this maybe later today, maybe tomorrow. We're going to talk about covalent molecules. But we're going to see, since we are talking about trends here, it kind of makes sense to talk about it. Certain elements will tend to kind of withdraw electrons when they are covalently bonded together. So we're going to see that, for example, we're going to learn how to draw these either again today or tomorrow. But this is what a water molecule looks like. And we're going to see that oxygen is more electronegative. Yeah, exactly. So it's going to hog the electrons. And so we're going to see that the electrons are going to move. I'm going to do this in a different color. Let's have green, yes. We're going to see that it's going to kind of hog the electrons it's sharing with hydrogen. So remember, ionic compounds, the electrons have pretty much completely gone over to the nonmetals. But in covalent compounds, we're going to see that those are shared electrons. And so we're going to see that because oxygen is more electronegative, it's going to kind of hog these electrons towards itself. And so as a result, it's going to get a little negative charge. That's a lowercase delta. And the hydrogen is going to be a little bit positive as a result. This part, don't worry about. This we're going to talk about next chapter. I just want to kind of show what this means in terms of like hogging electrons. So if you've done calculus, you might have seen delta as a partial derivative. And here it just means partial charge. So it's either plus or minus. Okay, don't worry about that for now, though. We're going to see that fluorine is the fluorine is going to be our most electronegative element. Right here's fluorine, as always. We're going to see it's exactly the same trend as all those other ones we saw. It's the same kind of idea about... Yeah, so that's going to be how we get polar molecules, but we're talking about that next chapter. So throw that out of your brain, because that's not on your exam on Monday, so don't even worry about that. Okay, so where were we? Oh, electronegativity, yes. So we're going to see that, again, fluorine is going to be our most electronegative, and so francium is going to kind of be our least, but we kind of exclude the noble gases here. These ones don't form covalent compounds. I mean, they rarely might, but they don't typically. So we don't really need to talk about them sharing electrons with other things. So fluorine is going to be our most electronegative, and francium is going to be the least for us. 1 second. Naughty ones. Ugh. What are you borking at? Ooh, I could have followers, primes, and views if I click this horrible link. Wow. Forget this. I'm going to skip teaching and become a... I don't know. Okay, forget it. Okay, so trend is exactly the same. It's based on effective nuclear charge, kind of like before. Fluorine has a very high effective nuclear charge, right? And so it's going to kind of try and withdraw electrons because those electrons would be more attracted to fluorine than they would be to whatever fluorine is bonded with. Okay, we'll talk about that next chapter. So again, you can dump it out of your brain for right now. Though maybe you shouldn't. Alrighty. Cool. Questions on electronegativity or electron affinity. So electron affinity doesn't have as nice of a trend, but typically we're going to see nonmetals have large exothermic affinities. Metals have kind of small, and they're going to be either endo or exothermic, and then noble gases do not want to gain electrons, so they are going to have endothermic ones. Okay. Coolio. Let's do it. All right, then our next thing. So we've already kind of talked about physical properties of metals and nonmetals, right? We know metals are shiny and silvery and tough, and you can bend them and make them into wires and stuff, and they conduct nicely. And we saw nonmetals are kind of the opposite of that. They're brittle, they don't conduct electricity, they are mostly gases, though they have all the states of matter could be represented there. And there are various different colors and all sorts of things. But let's talk about chemical properties now. We're going to see that metals, or metal oxides, are basic in water. So if we take, for example, how about magnesium oxide? If we put this in water, actually calcium oxide would be a better example. Magnesium oxide will work. We would technically get magnesium hydroxide, which is a base. Remember, OH compounds are bases. So exciting things there. We could also see that sometimes metal oxides can therefore react with acids. Will this one work? How about nickel? Yeah, nickel will work. We can react them with acids because typically we're going to see that metal oxides are basic, so we can react them with acids. We can see that that's going to create a salt and water just like any other neutralization. I was about to write H2O. Remember, this is a neutralization because it's producing liquid water. That is a neutralization reaction. Notice it's just a double displacement. There's nothing crazy here. Plain old double displacement. So metal oxides will act as bases. So we saw acids and bases do double displacement, and they produce a salt and water, which is a neutralization reaction. And so metal oxides will do the same thing. Very exciting. So sometimes your metal oxides will not dissolve in water, but you can get them to dissolve in acids. Just because they may not be strong enough or the hydroxides might be insoluble. But if you put them with acids, they'll form a salt that is going to be soluble. Hooray, how exciting. Guess what? If metal oxides are going to be basic, we're going to see non-metal oxides are acidic. And so if we combine a non-metal oxide with water, we get an acid. Right? This is carbonic acid. And maybe we remember carbonic acid is not very stable. It's going to break right back down again. But lo and behold, there it is. And since they are acidic, we can combine them with bases. And if we do that, we would get a salt and water just like before. So this is a neutralization. Just like before. We have an acid, a base, a salt, and water. Neutralization. How exciting. So, metal oxides are bases. Non-metal oxides are acids. So, do we think if we had to choose one of these to react with SO3, which one do we think is going to be the ideal one here. Yeah, right. So SO3 is a non-metal oxide, right? Sulfur is a non-metal, so we're going to see that if we were to combine this with water, that's sulfuric acid, right? It's a salt and water for neutralization. So, yeah. I don't know why I reacted with water. I'm sorry. I meant to react it with NaOH. I'm sorry. It's going to make probably... Is it going to make the sulfate or the sulfite? No, it'll make this. Yeah, we'll be good. Okay. So notice again here we have reacted with the base and we have made a salt and water. So we're predicting this one to be an acid, right? So sulfur trioxide would be an acid. Let's just see what would happen if we tried to react it with HCl. I don't even know what you would get. Not really sure. But this thing is not a salt, right? I'm not sure which sulfur and chlorine compound you would get. But it doesn't matter because salts have to be ionic compounds, right? That thing, SCl2 or whatever it happens to be, would be a molecular compound. That's not a salt. So this tells us that we're just putting two acids together. That's not going to make a reaction. So you can, I guess, test it that way. So, not going to happen. Alrighty. Questions about metal or and now chemical properties of metals or non-metals? This is very exciting, I know. Hi, little one. Okay. So the book has... Technically, it has, like, sections for each group of the periodic table. Yes, this will be. It's the last bit of our chapter. So, it does have sections on kind of the groups, though it's not typically very exciting. It's just kind of showing how these compounds come together. For example, we see alkali metals. They react in ways we've already seen them before. They form halides with halogens. They form bases with, I guess I need to, I'm really not balancing anything, am I? Shame on me. Oh well. There. They're pretty... I mean, if you really want to look over them, you can, but there's not a whole lot of new stuff there. So I'm kind of going to just skip that, if that's okay with you guys, since you've already seen it. So the homework that you have on these sections is stuff you've already seen. So, yeah. I mean, we already know that sodium forms a +1 ion. We know that calcium forms a +2 ion. Halogens form -1 ions. It's nothing new for us. So as long as you can remember that these alkali metals form +1 ions, you'll be okay. That's really the only thing from that section of the book. So, I mean, there are some cool like physical properties. Like sodium is actually really soft as a metal. Like you can cut it with a butter knife, no problem. And you know, it can react in these ways. It's pretty explosive. So it'll react with oxygen as well, forming peroxides and stuff. But again, it's kind of like niche stuff that's not terribly useful or exciting for us. So I say forget it. I'll give you a few homework problems on it, but that would be the extent of that. Oh, I just put you down, dude. You gotta behave. Okay, you're gonna come back up. Okay, cool. Unless y'all really want to see some, yes, that is exactly why. So, if anybody doesn't know, alkali and alkaline are kind of archaic terms that mean the opposite of acid. So, and you have an acidic solution or an alkaline solution. Alkali typically means base. So yes, that's exactly why they're called that, for sure. Okay. So, yes. Okay, so I'm going to post homework for this stuff. When I choose the problems, if I do see any that I think, oh crap, I guess I should have gone over that, we'll just do it tomorrow. But for now, this should be enough to get, I mean, it's really just going to be repeating the same stuff. So I would rather move on. So yeah, we already know that, you know, alkaline earth form plus, oops. They form 2+ ions. We know that halogens look, we've already done half the chapter. Hooray. Oz, if I put you down, are you going to behave? Please. Okay. Yeah. Hooray. Just so you know, there is something about noble gases that's interesting. And they pretty much only react with fluorine. So you can actually make fluorinated noble gases, but that's pretty much it. So fluorine is electronegative enough. It has a high enough, you know, a reactivity that it will actually react with noble gases, but it's pretty much the only thing that does. It's, you know, kind of a unique case. So you might see these compounds. I think we've actually seen them in previous little bits here, but again, nothing crazy. So it's all kind of niche stuff that is, you know, very specific. So I don't want you to really focus on that. So yeah. Cool. Forget it then. Actually, let me write this here. So we are done with exam 3 stuff. I remember. Yeah, you had asked about it was like a delta H problem or something related to one of these 3, but yeah, they exist. That's all you need to know. In fact, you don't even need to know that. Just assume every thing I give you will exist. So, hooray! So how are we feeling about exam 3 material? So it's just last chapter and this chapter. That's it. So it's the all the stuff with electrons. So, and then these periodic trends. So there's some kind of simple math. You're using equations like HC over lambda or whatever. I mean, this chapter right now didn't really have any math at all. Exactly. So we had some stuff with like bonding radius. Remember, we put those together and we made a bond, like a bond length. Exciting stuff. So, yes, I expect Usually exam 3 is easier. Actually, exam 2 is always harder, so exam 3 should be easier for you guys. So, yeah, I know. That means you need more homework, Shane. Don't make me. I'll do it. Actually, there is a practice exam up on Canvas for you guys. So, here, let's go ahead and have a look. Okay, let's see. Let's flip to this. Where are we? One of these guys. Down here, there is a practice exam that I have stolen, since I do not have a multiple choice exam for you to practice with. But lo and behold, we can see all sorts of fun stuff here. So the answers are at the back, so you can, judge yourselves. But it's the stuff here, it's almost all conceptual. There's nothing crazy going on here. So that is there for you guys to practice with. It's, exciting. So there we go. Where is this? So I know. So yeah, you'll have a practice exam for this, so you can play around. Alrighty. Yeah. I'm giving everyone 7 points if they did their homework. I just have not looked at that yet. So you'll get some points for that for free. Hooray! So that'll be adjusted when I get to the grading, if ever. Like the last day of the semester when I finally grade all your homeworks. That's when you'll get your points. Though I guess you all will technically all benefit from that, because if it's the last day of the semester, everybody's getting very easy grades. So, but yeah. Okay, anyways, back to new stuff then. Alrighty, so as always, throw questions in. Your homework will be due on Saturday, because I want you guys to see the key. So it will be due Saturday at midnight, or rather 11:59. Key will be posted at midnight. Okay, so that'll be posted later today, so you guys can work on that. And again, if I see any problems that I want you guys to do that I realize, oh crap, we have not covered this, we'll cover it tomorrow. Okay, but we should be in a good place right now. Alrighty. So, I guess if you guys want, on Thursday we can do another exam review, since this exam is kind of back-to-back with your last one. We can do that on Thursday if you guys want. So we can go over homework problems or whatever that we need to do. But again, this stuff, as we can see, is much easier than thermochemistry. Everything is. Okay, cool. So, bonding, let's just get rid of that. Oh. Okay, so for this next section, you can just ignore it until exam 4. So, hooray. Alrighty, we're going to see that we've kind of talked about ionic stuff already a ton, right? Electron affinity, ionization, blah, blah, blah. All these combination reactions and boring stuff. We're going to see that we're going to talk mostly about covalent bonding here. Because we also call molecules covalent compounds. And if we look at the word covalent, that means valence electrons, right? Valent. And then co means together, right? So these ones are actually going to share electrons. And those are always going to be shared in pairs. So we're going to be able to describe how molecules look using this concept of covalent bonding. So we're going to see structures like, we're going to be able to come up with this structure. We're going to be able to come up with this structure. We're going to be able to come up with this structure. We're going to have all sorts of fun structures to come up with. You know, we're going to have all sorts of fun stuff that we're going to deal with. So we're going to see these covalent molecules kind of look like this. So we see that these lines that we see here are all shared electron pairs. So we're going to be able to describe how these atoms are connected together in this chapter. So first things first, these are called Lewis structures. Based off a scientist named Lewis. And we're going to see that these structures are kind of going to be able to tell us a lot about the molecules themselves. So, first things first, we can display atoms by themselves. Right, these are just plain old atoms. And what we do is we include their valence electrons. And we represent them as little dots here. So we know sodium has 1 valence electron. Chlorine has 7 valence electrons, so that's why I've put them there. Technically, if we're drawing chlorines on, I'll go step by step. If chlorine has 7 valence electrons, we don't pair them up until we first have 4 of them by themselves, if that makes sense. So we're going to pair them up after the first 4. Yeah, we have fancy names for these. So it's just like how we didn't pair up the electrons in the orbital diagrams. It's the same idea here. Exactly, same thing. Yep. Alrighty, and so we can use these to kind of just display reactions a little bit more easily. So we can see that this electron here is going to basically go over to chlorine, resulting in sodium and the chloride ion. Technically, we draw these in brackets if they are charged. And so this would be how we could illustrate an ionic compound forming. It's boring. Who cares? We're done. I don't care. But covalent stuff, they take more work. I'm going to actually show you 2 ways to do it. You can use either way. They'll both work for you. The first way I like is a little bit easier, but the second way is a bit more traditional. So, first way. Here is carbon. I have drawn all the atoms here. So, by the way, this is methane, right? I've drawn all the atoms with their valence electrons. What I'm going to do is I'm going to make sure that every outer atom has all of its electrons that are going to get paired up with this central atom. And so I'm just identifying that we have valence electrons on all those hydrogens. That's one of them. And this carbon has 4 valence electrons. If 4 of those hydrogens are going to come in, we're going to be able to combine those into bonds. Like this. So where all of those were separate before, if we put them together, they are now shared. And so we often will just redraw this structure with lines, just because it's a little bit neater. So what I did was I took the actually, let me just do another example and then I'll kind of do a step by step. Let's take sulfur and oxygen. Okay, here's sulfur. All the oxygens are going to have 6 valence electrons as well. The goal of a Lewis structure is to make sure that your outer atoms have all their electrons paired off through chemical bonds. So, if we look at the oxygen on the right, we already have 2 pairs of electrons. Those ones are happy. However, we have 2 unpaired electrons. And we're going to see that those are therefore going to bond with sulfur. And we're going to go ahead and bond the other one as well. So now our oxygen will have everything paired off. That's what we want. If we look at the other oxygens, we have the same situation. We have paired off ones, and we have a couple unpaired ones. Those unpaired ones are going to also then have to bond with sulfur. And same thing here. We're just going to pair off our electrons. And as a result, we'll be left with this structure. So I think this is a fast way to get through these Lewis structures. And it only involves pairing off your electrons. So if you have unpaired electrons on outer atoms, bond them to the middle one. And that is all there is to it. Alrighty. But let's take a look at it another way. That is method 1. If we do method 2, that's okay. We're going to see, Kevin, that that is just fine. I'll explain that probably tomorrow. We will probably not have time for it today, but I will explain why we can have sulfur with 12 electrons later. Lewis structures are always going to be, exactly, it has an empty d orbital, so it can just plop electrons up into there. But oxygen wants to be, or outer atoms are always going to be more happy than the central atom. So we're going to see that's the case later. Method 2 involves a couple of steps. The first step is count up all valence electrons. So if we take our CH4, we know carbon has 4, and we have 4 hydrogens that all have 1 valence electron. And so that's going to give us 8 electrons total. Step 2 is assemble your skeleton. So that means just kind of draw your atoms around your central atom. Oh, by the way, the central atom is always going to be the first one given unless the first one given is hydrogen. Hydrogen can never be a central atom. So it's either the first one that's written, or I will tell you otherwise. It is also typically the least electronegative one that is in the middle, but that's another trend we'll see tomorrow. Oh my gosh, the creature jumped off the couch and now he's barking outside again. Shame on me. I'm an awful dog owner, apparently. So with this structure, we need to, since the whole point of this stuff is to show how these atoms are bonded together, everything is always bonded to the central atom. So we're going to need to put at least one pair of electrons between the outer atoms and the central atom. And so if we see here, we started with 8 electrons. That was our total. And we just used 8 electrons. We have no more electrons left to give. If we did, however, we would give them to outer atoms until the outer atom has 8 electrons. That's going to have a little asterisk. For hydrogen, it's 2 electrons. For beryllium, it's 4 electrons. And for boron, that's 6 electrons. These are the only exceptions to this. Everything else wants 8. So 3 exceptions. We're going to go through these rules, don't worry. I know I'm just blopping them out there, but we'll go through them. If you still have extra electrons, then we would give those to the central atom. And then the last thing would be adjust as necessary. And we're going to see that this would be possibly making double bonds or triple bonds as necessary. So if we wanted to take a look at a different one, actually let's make it a little easier. Carbon tetrachloride. First step is to count up the electrons. Which is 32. Yeah, I know. That's why it's boring. Who cares about methane? I don't like that problem. Let's do another one. Yeah, and so that's exactly why it's 8. So we have 32 electrons to mess with this time. So we want to assemble our skeleton. With a single bond in between here. So we have therefore used 8 electrons. We have 24 left. So now we have assembled our skeleton. Done. And we have accounted for those electrons. So now it says we're going to give extra electrons to the outer atoms until the outer atoms have 8. So chlorine right now has 2. Now it has 4, 6, 8 electrons. So I've just used another 6. Tells us we have 18 more. We're going to do the same thing for all the others. And the last two I'm just going to do at once because I think you guys can understand. I'm just putting 12 more electrons on. So we have now used all our electrons. We do not have any more. So we're not going to give any more to carbon. And now we're going to adjust as necessary. For this one, we're not going to need to. What adjusting means is that if any of them still do not have their 8 electrons, we would have to tweak our structure. So if we look at this, all of our chlorines have 8 electrons, and our carbon has 8 electrons. Everyone's happy. And so we are done. We do not need to adjust the structure. So we would just maybe redraw it a little bit more neatly. Okay, that works. Don't forget your electrons that are on your outer atoms. And this would be our completed structure. A few bits of terminology. This thing is called a lone pair. These are all lone pairs, the dots on the outside. And this is a shared pair, also called a bonding pair. If you were to do it the other way, by the way, naughty ones, if we draw our atoms with their valence electrons, we're going to get the same thing. I'm just kind of conveniently drawing my chlorine's valence electrons, but lo and behold, if we did this the other way, we just pair off our electrons that are not paired, and lo and behold, we're done. Everything that's left over is lone pairs, just like the other method. Okay, so we get the same answer using either method. It'll work. I think it's just easier to pair off your unpaired electrons. It gets you there much faster, in my opinion. But some people like to do this step by step, or maybe they learned it in high school or whatever this way to count out the electrons and deal with that. Oh my god. Well, it looks like we're out of time. And the dogs have officially just gone crazy. Yikes. Okay, so we'll continue this tomorrow. We are by no means done with this little topic of drawing these structures. We'll continue this tomorrow. So I'll post homework for you guys later. Your exam is going to be on Monday, so your homework is due Saturday. I guess that's it. So have fun. Enjoy your Monday. I'll see you all tomorrow.